Well, hello there. So today we're going to start a topic of circuit analysis that has to do with AC voltages and currents, which means they're sinusoids, sine waves for all of our voltage sources and current sources. And this is usually called phasor circuit analysis, as we'll see, because a phasor concept is important to finding these solutions. AC steady state or phasor solution is when we have sources like this that are sine waves. So cosine omega t plus phi has a frequency omega in radians per second. Phi here is the phase angle. And we're looking, it's important to realize we're throwing out the transient response. So if we turned this sine wave on, there would be a transient where everything comes to steady state. But in the end, all of the responses are going to be some form of sine wave themselves. And so we're looking at the steady state version where the transient, the homogeneous solution to the differential equation has decayed away to zero. This is still really useful because AC power is the most common source of power in buildings and things like that. So you'll see this a lot in large motors and all kinds of analysis. And the steady state is a limitation, but it's really the most common state because once we turn it on, it achieves steady state relatively quickly in most cases. The other thing we can see from this is with the Fourier series, which is another math transformation, you can represent any signal as a sum of sinusoids. So this has more general use as well. The great thing about phasor analysis is that it doesn't require differential equations. So to solve in general in the time domain, you're solving a system of differential equations when you have inductors and capacitors, and that's tricky and takes a lot of math skills. So this lecture is going to cover a lot of the math background that you need in order to do phasor circuit analysis, and we'll do some very basic circuit analysis towards the end. So starting off, our assumption is that all of our sources, current sources and voltage sources, have equations like this. They're a cosine or a sine. They have a frequency omega. The frequency, if you have more than one source, all the frequencies have to be the same. You can handle it using superposition if they're not, but in our case, we're going to start with all same omegas everywhere. They can have different phase angles and different amplitudes. When we graph a cosine wave like this, it starts off at Vm, the amplitude at time t equals 0, and we have a frequency f or a frequency omega. F would be in hertz, cycles per second, and omega would be in radians per second. There are some useful trig functions to remember. The most useful one is right here at the top. If we have a sine function, we can represent it as a cosine function by subtracting a phase of 90 degrees. So sine x is cosine x minus 90. And we're going to convert all the sine waves to cosine waves just as a standard. When you do phasor analysis, you'll hear lead and lag used a lot. And that is talking about the phase angle, this phase angle right here that comes in to our cosine function. That's a shift because what happens at t equals 0 is shifted by this. And you can see that in a graph. So in the baseline, this blue one, this has 0 phase shift. So the phi is 0 there. And if we add or subtract pi over 4, V1 has negative pi over 4 phase. That's the red here. And it's coming after. This is t equals 0. This is later, so its peak comes after, so we say it lags. Negative phase shift lags. V3 here in green has a positive pi over 4, so to make this whole term 0, t would have to be negative, and that's why the peak happens over here on the negative side of the x-axis. And that's a shift where it's moving in front. It happens before. Its peak happens at t less than 0, the baseline happens at t equals 0, the lag happens for t greater than 0. So this is leading. So with a positive phase shift here, you see that this leads. So the reason we do phasor math here is it's a math trick that keeps us from having to do differential equations. That's the main reason we like it. So it's a domain transformation. So we take an equation and transform it into a different kind of math equation that's easier to solve. So the phasor technique takes us from the time domain to the phasor domain. And when we make that transformation, integral differential equations become linear equations. And that's the big advantage to this technique, is that we don't have to solve differential equations. We can solve linear equations again, which we like, which we were doing before with just resistor circuits. Once we added in capacitors and inductors, we had differential equations. And so this lets us do capacitors and inductors and resistors and keep it all linear. So we transform the equation, transform the circuit, then solve for whatever we're interested in, and then we convert it back. We inverse transform. So sinusoids, trig functions, are also related to exponential functions using Euler's equation here. So Euler's equation says that e to the j theta is cosine theta plus j sine theta. And here we're going to do the electrical engineering standard where j is the imaginary number square root of -1. In most math classes and in MATLAB and things like that on your calculator as well, it's going to be I, but I is so overused because we can't use I for inductance, we use L for inductance, but I is current in circuit analysis. So here we use J. So most electrical engineers use J instead of I for the imaginary number. And MATLAB is happy with either, actually. You can use J or I. So this lets us turn cosine functions into exponential functions, which makes the some of the differential equations and everything work out a little bit easier. So when we have something in this form, it's got an amplitude of 1 in this case and a phase of theta in this case. We can also write this polar with an amplitude and a phase as a rectangular with a real part and an imaginary part. So if we have a general complex number has a real part x plus j times the imaginary part y, these functions re of a complex number gives us the real part, and im of a complex number gives us the imaginary part. So these are functions in MATLAB, and it's just part of the math lingo that we're trying to get through today. So once we start with Euler's equation here, we have these rectangular coordinate form, which is the real and imaginary part, and we can graph that on the complex plane. So the complex plane has an imaginary axis, usually the y-axis, and a real axis is the x-axis here. And so we can go, to find our z, we can go over x, and we can go up y, and that's our complex number. But we could also represent this in polar form by going out z, the magnitude, the length of this vector, go out all the way to here, and then rotate up theta. So that's a polar form. And this exponential form is naturally in the polar form with the magnitude z and angle theta in radians, or x and y, rectangular coordinates. So these are both ways to represent a complex number, and we'll use them both because sometimes math is easier using the rectangular form, sometimes it's easier using the polar form, and there are conversion equations right here, and they're based on this triangle. So x is z cosine theta, y is z sine theta, z is from the Pythagorean theorem, and theta is the arctangent of y over x. The polar form, we're used to the amplitude or the magnitude here and the angle with this little angle sign in between. This, I think, is the most common way that you'll see phasors written because it directly maps to the cosine term. Our book likes this form, and so they use it quite a bit. I've tried to update the notes to show both here, but amplitude and phase. So it's just the two numbers that you're worried about. So either amplitude with the little angle sign and phase, or amplitude and E and a J and then the phase. It's just kind of a boilerplate either way. But this reminds you where the math comes from. This is a little more compact and reminds you of the important parameters. So, all right, so here are complex number identities, equations, and things like that. So there are a lot here. You're going to really want to be good at this, and normally with a calculator or a MATLAB computer that can do complex numbers. Most of your graphing calculators are happy with complex numbers too, so you can find there's a little I button somewhere in your graphing calculator. But this is the basis for cosines to exponentials, adding complex numbers z1 plus z2. You add the real parts and you add the imaginary parts together. For multiplication and division, you multiply the magnitudes and add the phases, or divide the magnitudes and subtract the phases. So those are things that will come up all the time here. It's important to remember some of these things, like what happens, j squared is -1, so you can flip the sign and things. So there are a lot of things that are in here, and we'll see them repeated over and over again. So you should, if you're not familiar with these, if you've never seen them before, you'll probably want to do some review from our book. So I'll show you the really important ones here. The transformation from the time domain, where we have a cosine function like this, amplitude, frequency, and phase, v0 cosine omega t plus phi, we transform that by writing it out like this. The real part of this, which is from the Euler equation, but you can see we're just copying down certain parts. So the amplitude v0 comes here, the phase comes here, and the frequency comes here. And then we take this first bit, v0, with the amplitude and the phase, and that's the phasor part. And that's the part that we care about, because that will come into all of our analysis. And the rest of the parts, the real part and this omega t part, they just kind of hang around on the edges, and we put them back in at the end. So we transform, scrape it away, use the phasors, and then push it back together at the end. So here, if we have v0 cosine omega t, our transform is just v0, or v0 with a phase of 0 is the way I would write it, or v0 e to the j 0. That's where we get the v0 here. The general term v0 cosine omega t plus phi, you can see we just put the v0 here and the phi here, or the v0 here and the phi here. So we're just keeping track of those. Omega comes in, it's important, don't forget what it is, but it's not part of the phasor transform right here. So if we had a phase shift of negative pi over 2, then it would be written like this: amplitude or magnitude and phase, negative pi over 2, or amplitude and phase. A very common thing that is completely wrong in terms of the physics, but still very common because of the fact that we kind of leave out omega when we talk about phase. Often phase is talked about in degrees, but omega is in radians per second because it's in calculus, and so we keep things in radians for calculus. And so it's very common for an answer to a phasor problem to look like this: amplitude A cosine omega t, where omega is in radians per second, and a phase shift of -90 degrees. So radians per second times seconds will give radians here and degrees here. So you can't solve this. It's all the wrong units. But because we really care about the phase and the amplitude more than anything else, this is still really commonly used, and you'll see that when people are doing phasor analysis. So you just kind of get used to it, even though it's not technically correct. Okay, so here's a table of a bunch of transforms that going from the time domain to the phasor domain. So A with a phase of phi becomes A e to the j phi, or we can just write it A with that angle sign and phi. The other really important one here is this: the derivative of a function is j omega times the transform of the function. So if we have cosine omega t plus phi, when we take the derivative of it, there was that e to the j omega t part that was floating around alongside. I can find it back here, j omega t. Here's where the time derivative part comes. So we have a j omega that comes out from the chain rule. So the derivative is j omega times that. So you'll see this coming up soon. Integral 1 over j omega. So a lot of math that you've seen here, and we're going to keep going. So work some examples, get familiar with this. If you have to look up every math trick, or if you get stuck in the math and can't solve it, you can't get to the answers. So working a lot of examples and asking for help if you need it is going to be a useful thing. Don't just your way through this math. All right, so this is a summary. These hand-drawn ones are from a different are from slides that I made another time. So these are the ones that are important to remember, the hand-sketched ones. So our basic transform, a cosine omega t plus theta transforms to a with a phase of theta. And you have to keep track of omega, but it doesn't show up in the main transform. From a with a phase of theta, that's the polar form. We can also transform to the rectangular form, lowercase a plus j times b. And the equations to transform back and forth, either from the triangle here, a is the real part, b is the imaginary part, capital A is the amplitude, and theta is the angle. So the triangle gives us these equations and these equations. There's a very common mistake, this note down here, when you're using inverse tangent, arctangent here, on your calculator, you can get the wrong answer. And the reason is because arctangent takes a single number, but it's the ratio. Arctangent of -1 over 1, the arctangent of -1, that means b is -1 and a is +1. So we're over here, and that would be our theta. Not sure where the spikes come in. But in your calculator, arctangent of -1 could come from this, where b is +1, we're up here, and a is -1, and that's this angle. And you can see they're not the same, they're 180 degrees off. So if you're using arctangent on your calculator, or in MATLAB, or in C, or something like that, Python, be careful with that. There's always a function called atan2 in every programming language, like MATLAB, and MATLAB has another function called angle that you'll see me use a lot. atan2 takes the numerator and the denominator separately, so it gives you the right quadrant, and that's what it's for. So make sure you're using that one. If you're just doing it on your calculator, generally just sketching it and fixing it by adding or subtracting 180, you figure out which quadrant you're in. And then if you get an angle like -45, when you really know it should be something like 135, you just add 180 in, and off you go. So that's the caution on arctangent. Okay, so Phasor Arithmetic, this was on the previous slide, but this is just the important summary. So when we're adding or subtracting phasors, then we want to use the rectangular form, is by far the easiest one, because this is a phasor in rectangular form and another one in rectangular form, and you just add the real parts and add the imaginary parts, and you've got a new phasor in rectangular form. They add graphically because they're vectors like this. You can think of adding the x components and the y components to get a total vector. This rectangular form I think is best for MATLAB and calculators, so generally I would do everything in rectangular form. The only drawback is that we need polar form, because that's the cosine. When we go back to the time domain, we have to put it back in the polar form because we need an amplitude and a phase. But for adding, definitely use rectangular form. In multiplication and division, the polar form is easiest, and this comes back to the exponential derivation. But if you have amplitude with a phase of theta, a with a phase of theta, times b with a phase of phi, you multiply the amplitudes and add the phases to get your answer. And dividing, you divide the amplitudes and you subtract the bottom from the top, alpha minus beta for the phase here. And 1 over, sometimes we do this for the 1 over. The 1 overs comes up a lot, as you'll see. We have amplitude of 1 over the amplitude, and this was 1 with a phase of 0, so 0 minus gamma, I guess that is, negative phase there. You can multiply and divide in rectangular form by just expanding the parentheses. So 3 times 6 plus 4j times 6 plus 3 times 7j, collecting all the terms and remembering that j squared becomes -1. You get this. And MATLAB is happy to do this as well. Multiply and divide in rectangular form on your calculator just fine. But if you're doing it by hand, the polar form makes sense. All right, so that is a summary of the math behind phasors and sort of the justification why phasors is a good thing. It gets rid of differential equations. It will transform our equations back to linear sets of equations for our circuits with complex numbers, but that's a good trade-off. It does ignore the transient solution, which decays to 0 in a few time constants, so it's an okay thing to ignore. So we'll use all of this in the next video to solve some circuit problems. See you then.